Hello, calculus students. Unfortunately, I am still at jury duty, so I'm going to record a series of videos here to take you through the remaining topics in Unit 10A. That way you'll be able to self-study even though I'm not here and stay on pace to complete the curriculum and be ready to take your assessments, hopefully. We're going to start with topic 10.7, which is on page 13 of your notes packet. So if you'd find that, that's where we'll begin. We're going to talk about the alternating series test for convergence, which is going to be especially useful for series that have some kind of alternating component. You'll see that most commonly as a -1 raised to a power related to n. And so what that does is if it's combined with an a sub n formula that creates positive terms, then it will cause your terms in your series to alternate back and forth between positive and negative. Sometimes the first term will be positive, sometimes the first term will be negative, but the idea is that those terms will alternate back and forth. So because of that alternating behavior, we have an alternating series test that's designed to help us determine whether or not this series is going to converge or diverge. So again, the actual series part, if we remove the alternating piece, needs to have terms that are greater than 0. And then we've got two different ways to write that based on being raised to the n power if we start with 1 or n plus 1 power. So that's positive term first versus negative term first. But the two things we need to check for to see if that series is going to converge is going to be limit as n approaches infinity of the way the terms are defined, but with the alternating component removed. So this is very similar to like an nth term test type thinking, but we take away that thing that's creating the positive and negative signs to flip-flop back and forth. The condition that we're looking for is that those terms are getting smaller and smaller, so they're approaching 0. Now remember, if this was a straight nth term test, that would be a situation where things are inconclusive. So just keep in mind that we're doing something different here. We're looking at that part of the series formula that removes the alternating piece, and we're looking for whether those terms get smaller and smaller. If that condition is met, then the second thing that we need is that we need the a sub n plus 1 term to be less than or equal to the a sub n term. So basically that means that our a sub n values are non-increasing. They might stay the same or they might decrease, but they can't increase. So if we know our terms are approaching 0 and we know they're either staying the same size or getting smaller as we go through the series, then we'll be able to say that the series converges by the alternating series test. We're going to look at some examples. So go ahead and flip to page 14 and we'll continue on seeing how this test looks in action. All right, our first examples here are going to ask us to use this alternating series test to determine convergence or divergence. It is true that if we don't meet the conditions of the alternating series test, that the series diverges. So it's not going to give us an inconclusive situation like we have with our nth term test, for example. Okay, first things first. Without the alternating piece, we're supposed to check to make sure that our terms are greater than 0. So it is true that 1 over n is greater than 0. So we've met that original condition that a sub n is greater than 0 for all of our n values. Then we continue to the two parts of the actual test. So the first condition that we need to look for, again, ignoring that alternating piece, is that the limit as n approaches infinity of a sub n has to approach 0. Which in this case, 1 divided by a very large number will do just that. So we have satisfied the first condition of the alternating series test. The second condition is a little bit tricky to test sometimes, but remember, we're thinking about the n plus 1 term, and we're comparing it to the nth term. So if we imagine replacing n with n plus 1, we can compare that to what would be true if we plugged in an n. That's just the little definition that's sitting here. And what we're trying to determine is whether or not the n plus 1 term is less than or equal to the nth term. So we don't technically know right now whether or not this is true, but we can do a quick little investigation, like a cross-multiply type deal. N is less than or equal to n plus 1 would be the result of that. And then I think it's pretty clear that that's true. But if you're still not 100% certain, get all the variables on the same side. That would leave behind 0 is less than or equal to 1, which for sure is a true statement. So we've now satisfied the second criteria of the alternating series test. So that means that this series converges by the alternating series test. All right, let's go ahead and look at part B and see if we end up with a similar situation. Remember, without that alternating piece, we need to make sure that our a sub n, which is n over n plus 1, is always positive, which it is. If we start with an n value of 1, the numerator and the denominator will always be positive. So we've met our initial condition, and now we start by testing the two criteria. So we need the limit of a sub n as n approaches infinity. I'm noticing that these powers match, so the ratio of the coefficients is equal to 1. That is not equal to 0. So we have failed the first condition of the alternating series test. We did not approach 0 as n approached infinity. We approached something else. So this means that the series diverges by the alternating series test. Okay. In this box, you'll see that there's a couple of different ways to verify criteria number 2. So we plugged in the n plus 1 value for n to see what that a sub n plus 1 term was and compared it to the a sub n term. That's looking at what's happening here. We just set it up and then worried about the subtraction at the end. Another way to do that is to look at the ratio between the terms. If the ratio between the terms is less than or equal to 1, then that means that they either match or the top one is getting smaller, which is what we're looking for. So you could approach it that way. Or if you really wanted to, you could use derivatives of related functions, replacing those n's with x's. You would be looking for the derivative to be less than or equal to 0. That would tell us that it's decreasing or at least remaining the same. So a couple different options that you have for how to test that second criteria to make sure that the terms are either staying the same or getting smaller, that they're non-increasing. Okay, we're going to take it one more example for this particular topic, and then I will end this video and I'll move into the next topic, and you can practice this one first and watch that one later if you want to, or you can go right into the notes for the next topic if you'd like. We are going to skip example 3 down here. It does have a typo, so if you want to investigate example 3, replace this n that's down here at the bottom. It should have been a pi symbol, but somehow it ended up being an n instead of a pi. So that should be 2n minus 1 times pi. But we're not going to worry about that one for today. Just focus on example 2. Okay, example 2 is the same. We're going to show that this series is an alternating series that converges. So we can see the alternating part of it here. If n is equal to 1, it's going to have a negative value, but if n is equal to 2, that will flip to be positive. 2n factorial is always positive. So sure enough, we're going to be in an alternating series situation. I'm going to show that I checked that my a sub n, which again is 1 over 2n factorial, is greater than 0, which opens me up to test the two criteria for the alternating series test. So up first, I need to think about the limit as n approaches infinity of this series, but with the alternating component removed. So just the 1 over 2n factorial part of that. 2n factorial as n approaches infinity is going to grow without bound, and 1 divided by a very, very large number is going to approach 0. So we have met our criteria for that first portion of the alternating series test. The second portion of the test, remember, has us compare the n plus 1 term to the nth term. This is going to get a little bit messy. I'm actually going to use this ratio test just to show you another way of approaching it. So I'm going to think about what the term would be when we plug in n plus 1 for all of the n's, but again with the alternating piece gone. That's going to look like 1 over This n is inside this factorial, so that n plus 1 is going to live right there next to the 2, and then the factorial is going to be on the outside of that. So just be careful there with your order of operations when you're writing out what the n plus 1 term is. We'll do some simplifying with that in a minute, but I'm going to finish my ratio up first. I need my nth term to follow that up. So that's going to be 1 over just n plugged in, which looks like my original series formula, but with that alternating piece removed. Now this is a little bit of a mess, but if we think about multiplying by the reciprocal, I'm going to go ahead and distribute this 2 at the same time because all of this expression is going to have a factorial applied to it. So 2 times n plus 1 is really 2n plus 2 factorial. And then we're going to multiply by the reciprocal. So this 2n factorial is going to move to the numerator. Now, I don't know how much you remember about factorials, but if we start listing out terms of a factorial, we end up decreasing by 1 each time. So the first term of this factorial is 2n plus 2, and then we multiply by 1 less, 2n plus 1, and then we multiply by 1 less, which would be 2n, and then 2n minus 1, and 2n minus 2, and 2n minus 3, and we keep going, but all of those remaining terms are really 2n factorial. So we kind of peeled off these first 2 terms from this factorial, which allows us to leave 2n factorial in the denominator, which then cancels with our 2n factorial in the numerator. And so what we're able to do is we're able to rewrite this ratio as 1 over 2n plus 2 times 2n plus 1. The factorials are gone. Now keep in mind what we were doing. We were finding the ratio of the nth plus 1 term to the nth term. And if we think about this as n gets really, really big, because that's what's happening, that is most definitely going to be less than 1 because we're doing 1 divided by a very, very large amount. Okay? That means we verified that our terms are non-increasing using this ratio. And so we've met the second criteria of the alternating series test. That means we're ready for our conclusion. The series converges. We met both criteria. So that series converges by the alternating series test. Okay, that's going to be it for our examples for topic 10.7. So again, like I said, if you want to stop and do some practice with 10.7, feel free. Otherwise, go ahead and continue on to the next video and continue your study. We've got a couple more topics to cover today.